All right, and we're back for the last chunk or two of podcasts dealing with fiber optic. I'm just reminding you here our basic cable types. We so far have covered coax, non-paired, balanced twisted pair. The last two are multi-mode and single mode, and that's what we're going to focus on these podcasts here. All right, so general, where am I typically going to find fiber optic? It's typically going to be backbone wiring between my closets, between my switches, if you will. This is not very common as a horizontal wiring, if you will. That's where your twisted pair has the kind of the dominance. But it is acceptable. I can use it as horizontal cabling out to my desktop if I want to. It is acceptable, but I'm typically going to find it as my backbone cabling between my closets. Advantages of fiber: it does not generate; it's not susceptible to EMI. It does have high bandwidth with long distances, and I don't have. It's not a conductive fiber. So I don't have any issues with it transmitting electrical problems from floor to floor, if you will. Disadvantages is it is more expensive than twisted pair. It requires more expensive workstations, outlets, or workstation configurations and outlet configurations. It's more difficult and time-consuming to deal with and terminate. More difficult to test and need specialized equipment, etc., etc. It's very fragile. So there's some disadvantages. So that kind of leads to I'm going to use twisted pair pretty much throughout my building. So when do I need to use fiber instead of copper? That's kind of, excuse me, that's kind of what it boils down to. Where do I need to use fiber instead of copper? I like to approach it this way. A lot of times in today's budgets in networks and IT departments, you have to justify everything. So if you're going to put fiber in, there needs to be some kind of justifiable reason to do it. So one of the reasons is if it's going through a high noise EMI RFI area, just a pair is susceptible to it. Fiber optic is not. If I need to go beyond 100 meters, twisted pair is limited to 100 meters. If I have to go beyond 100 meters, I pretty much need fiber to do it. I can do 300, 400, 500 meters with just plain old multi-mode fiber. I can move over to single mode and get a few kilometers if I need to. Typically, between my floors or closets in my building, I'm going to use fiber. Fiber being glass, it's an insulator. So if I connect my two data closets in my building between two floors in my building, being an insulator, it's not going to transmit any electrical problems from one floor down to another floor. That can happen. Electricity always finds the path of least resistance. So it's good to isolate my closets, electrical isolation between my closets or between my floors, if you will. And sometimes in high security areas, fiber is used because I can't readily tap into fiber. I always like to think of fiber as almost like a water pipe. If I drill into a water pipe, you're going to know. Again, I'm up in the bathroom taking a shower, somebody drills in the water pipe, I'm going to know because all of a sudden the water pressure drops. So in high security areas, sometimes fiber is used for that security reason. All right, general construction of fiber. One or more buffer coated optical fibers made of extruded glass, enclosed in protective outer jacket, fiber strength members, buffers. Okay, we're going to show you a picture of that in just a minute. There is plastic fiber out there, but it's not really blessed by the wiring standards, so most things are glass. And I like to think of it almost as a light pipe. Almost think of it as a light pipe. Just kind of keep that little in the back of your brain. That's going to help with visualizing a lot of this stuff. Most of the fiber we're going to deal with is going to come in two strands. One is a send, one is a receive. Or you can almost think of this as northbound lane on a highway, and the other one's the southbound lane on a highway. That's typically how we're going to find our fiber connections. Two fiber strands. One for send, one for receive. Here is where we're going to zoom in on the construction of the fiber. If I start, actually I'll start up here at the cable jacket. This is the visual part. Typically in multi-mode fiber it's going to be orange. If I cut that insulation away, the next thing I find, and that's there for protection. I can label the insulation as protection, all that kind of good stuff. And as I cut that insulation away, I'm going to find these typically yellowish hairs. These are strength fibers. These are there for strength. as I'm installing the fiber, giving it a little bit of rigidity as I go to try to pull in the fiber. It's giving me some strength so I don't break the glass inside. These are typically Kevlar strands for strength. As I cut that away, I'm now going to find the actual glass stub. Now, the glass stub itself, this is about the size of a human hair. And that glass stub, if I were to look at it under a microscope, is actually made up of two pieces of glass. The outer piece of glass is the cladding. The inner piece of glass is the core. Now, we're going to get into the details of this in Chapter 11, but just to get you kind of a ballpark, they actually make this in a process where they control the cladding glass and the core glass. It's actually two different pieces of glass that they kind of put together. They control how they're made, and the cladding has a higher refractive index in the core. The core is designed to carry the light signal, and the cladding is designed to bend the light back into the core, almost like the I like to think of it as a garden hose. The hose itself is designed to keep the water in the center of the hose. So the cladding is acting like the garden hose, and the core is kind of the hole in the garden hose. And that's kind of what they do to make the two pieces of glass. They actually take a tube, and then they do a very specific process to get the glass in the middle of that tube, almost like the jelly filling. Jelly filling. Okay, but that actual glass stub, the core and cladding all together, is about the size of a human hair. But if I were to look under a magnifying glass, I would see those two distinct, the cladding around the outside, almost like the outside of a hose, garden hose, and the core in the middle. There is actually two different types of fiber when I start getting into it. There's tight buffer and loose buffer. Tight buffer is the outer insulation is actually adhered to the copper fiber, if you will. I have copper wire in here. Okay, surrounds the fiber and here's the fiber, like insulation attached to a copper wire. Or loose buffer, the actual glass fiber is loose in a tube. So if I take a look at these, here is tight buffer. This is typically the fiber we would find, multi-mode fiber. This insulation here, the orange and the blue insulation, are actually adhered to that glass stub. Meanwhile, something in typically a single mode, these glass fibers are free to move about in a straw or a tube in a loose buffer mechanism. So we're typically going to find this in multi-mode. That's most of the stuff we're going to find. But every now and then you might get into some single mode that actually has a loose buffer like so. Another way you categorize differences is multi-mode and single mode. So let's get into the two types of fiber. Multi-mode is going to transfer data through the core using multiple light rays. A fancy name for a light ray is a mode of light. So it's a multi-mode. My light signal is made up of multiple rays of light, multiple light rays, multiple modes. So a pulse of light goes down the fiber, and that's why they're showing you all these different light rays. A pulse of light goes down the fiber to represent a 1, followed by no pulse to represent a 0, followed by another pulse to represent a 1. Well, that pulse of light that's representing the 1 is made up of multiple light rays, multiple modes of light. Henceforth, it's a multi-mode fiber. A multi-mode fiber, the core diameter is around the 50 to 62 micron in diameter. We'll get to that size here in a few minutes. The cable lengths for multi-mode are relatively short, 300 to 500 meter ballpark. Depends on the type of fiber and the light source you're using. This is typically for LAN, between switches, between routers, between closets in my building or in my network. It's typically where I'm going to find multi-mode. That's what we said earlier with LANs. This is the stuff you guys are probably going to run into in networks, multi-mode fiber. And the light source for this is typically an LED light source, relatively inexpensive, built into my optics in a small form pluggable module and a switch. Ooh, it's getting late. That's typically what you're going to find. Meanwhile, a single mode fiber, the name is telling you single mode, single ray of light, single mode of light. It's going to transfer a signal through fiber using a single ray of light. And for that, I'm typically going to use a laser light source, because even a generic little laser pointer can generate a distinct fine point of light even a great distance off. So my light source for this is typically going to be a laser light source, so that I can go down a core that's around 8 to 10 microns. Again, we'll get to that size in a minute. So this one I can ship a large amounts of data, and I can go great distances. I have a super small core and a super fine directed beam of light, so I'm not giving it room to expand, so it can go great distances. Well, we're in the tens of kilometers plus, easily. So I'm typically going to find this for WAN use, single mode fiber for WAN use. All right, let's dig a little bit deeper into the multi-mode single mode thing. Multi-mode, there is graded and step index. We'll talk about that in a minute. Laser light emitting diode for my light source, and as that pulse of light goes into the fiber, all those light rays are coached down the fiber by the indices of refraction. The fiber itself, as we said, the core and cladding, the two parts of the fiber, the core and cladding, have different indexes of refraction. If you think back to maybe science class where you took a beaker of water and you put a pencil in, when you put a pencil into the water, it looked like the pencil was kind of split in half, because as I was going from air to water, the light rays bent, so it looks like the pencil got bent or broken, mainly because the light and air had different indexes of refraction. So as the light went through, it looked like it was broken. It was just bending the light rays, is all it was really doing. Well, my core and cladding have different indices of refraction, and the core, as the light tries to leave the core, the cladding has a different index of refraction. It's going to try to bend it and keep it back into the core. It's going to play goalie, if you will, and keep it in play. So as I look at this, introduces light at all angles, and is coached down the fiber by the gradient of refraction. That's exactly right. The cladding is going to bend it and keep it back in the core. So my multi-mode is using the LED light source, typically in the 850 nanometer to 1300 nanometer wavelength. Again, we'll get into some more details of that later in the fiber optic chapter. Meanwhile, single mode, is the transmitting emitter is a laser diode. Light entering the fiber is straight, coherent along the axis. And my light source for this is typically 1310 nanometers to 1550 nanometer light source for this one. Here is pictures again of single mode, multi-mode. Okay, single mode, I'm sending a single ray of light down through my core. Multi-mode, I'm sending multiple light rays. I'm either bending them to keep them in the core, or my index of refraction is drastically different, and it's actually bouncing off, reflecting off, if you will. And that's where they get the graded index and the step index on those two. And here is your common sizes then. So as I look at multi-mode, I typically run into 50 125 and 62.5 125. When I look at those two numbers, it's telling you the core diameter and the cladding diameter. 50 microns core, 125 micron cladding, or 62.5 micron core to 125 micron cladding. That's what that's showing you. And as I look at 50 125, that's your graded index. 62.5 125, that's your step. And if I go back here, your graded index is the one that is actually trying to bend the light rays and keep them in the core. The step index, or the 62.5, it's a dramatic difference in index refraction. It's bouncing the light almost like a mirror back into the core. It's a lot harsher. So we'll find out later the step index, or 62.5, does not have a great as range as your 50 125 graded index. Meanwhile, your single mode is in the 8 to 10 micron core and 125 micron cladding. Much smaller, much smaller. So as I look at a size comparison, here's trying to show you a quick size comparison of step index, graded index down to single mode. Just trying to give you a little relationship on size there. Meanwhile, here's a quick math. Again, you don't need to know all this math, but I'm trying to put a micron in perspective for you. As you go down through, micron is 1/1 millionth of a meter, or 10 to the negative 6. If you keep going, 62.5, the core is around 2 to 3 thousandths of an inch, and the cladding is around 4 to 5 thousandths of an inch. Well, that's not a lot of perspective for us, but if I look at an ordinary piece of paper laying on my table, that's typically around 4 thousandths of an inch. So the outer diameter of my fiber optic, the cladding, being 125 microns, is about the thickness of a piece of copy paper, or are a little bit thinner than a human hair in many cases. So we're talking about very small stuff. The cladding is about the thickness of a piece of paper, and the core is even smaller inside of that. So very small stuff. Again, just trying to put it in perspective for you. We'll come back on the next one.